Okay, so torsion, what does it mean? Say someone, your friend, who hold your hand, and he is pulling. So that will be axial, but he trying to twist like that, right? That means if he has too much force and twisting the high force, right over here your joint will be detached. Okay, so that kind of load is called twisting. And normally, say you have a soft pencil, it's a very brittle material, right? You do like that, you see ultimately it becomes two part. So in industry or in engineering application, we have lot of parts that carry torsional load. For example, uh, you see the empty chassis of a truck. They have a shaft going from engine to the rear axle, little bit inclined, right? But that is rotate and transmit power from engine to the differential gear in rear axle, and that's how you turn the wheel. So that is one application. Other application you might see that with one engine you are driving multiple things. Say you have icing right over here, and you have a shaft. In the shaft you have multiple pulley, and right over here one more shaft you have your something over here. Okay? It has a pulley also over here, and this pulley is run by belt. Okay, this one has a pulley. Normally example I giving you, when I was in school or high school, I see the village area, they have rice mill, you boil the rice, say you have 80 kg of rice, take there, they take care of it. They give you the, take out the outer shell. It's called rice mill, Bangla, Dhanbanga machine, right? And I see same use the bigger IC engine, but they are driving multiple machines with the hauler, ice hauler. So, but I'm saying there's a lot of application of this one. Now, if you apply a torque means two opposite torque, right? Say this is rod, left end is fixed, I'm fixed, I'm trying to twist, then what will happen? Still, it will, if it's very weak, if you apply very high load, then it will become just two part. Experimentally, you can prove it. Example, you take stock pencil and hold on and do like that, or it do just like that. If I hold it, what happens? I'm trying to twist this way, but due to the support, you will apply torque in opposite direction of this torque. So similarly, if you take a soft pencil, you do like that, it automatically will break down. Okay, that means due to the torque, how a material become two part, because shear force part there, and that's why it become two part. Similarly, I can show you a figure right over here. This is example that where we apply the torque, but see right over here, it's a ductile shaft. This is also brittle, but almost same diameter. If you apply torque, brittle material fail like that, become two part, and ductile material not 45 degree, little bit 90-degree angle. Okay, just you remember how a traction become two part, because shear force or shear stress become dominant. Dominant means become higher. That's why it failed. So we are applying only torque. What is the definition of torque and bending moment? Almost same, right? Because bending moment it will depend by M. M unit is Newton meter, right? Newton meter. And torque T also unit Newton meter. But there is a difference. Due to the bending moment, your stress will be sigma equal to MC over I, that we learn in beam section, right? But if you, and due to the bending moment, your beam will bend like that. right? If it is horizontal, it will be line. But due to the torque, there will be two things. Number one things, if torque is very high, it generates shear stress inside the material. If that shear stress become higher than the material resistance, then material fail. If less than the resistance, then material will not fail. So I am applying torque, but inside develop shear stress now. So I need to measure this one. How you can do it? From the inside, you cannot measure, right? So we need to have a formula. That formula is tau equal to TR divided by J. And this will be derived with section B. And you look the video and you easily understand. So this is shear stress. This is the torque. Torque you can see, we apply external, but tau we cannot see. J is polar moment of inertia. So what is the value of the J? J equal to pi by 32. If this is solid shaft, then d to the power 4. This is your J. And what is R? R equal to d by 2. Outer radius divided by 2. Now this formula is only applicable for a circular shaft, hollow and solid shaft. Now, if you look carefully this formula, that shear stress tau equal to TR by J. Excuse me. TR by J. So this is my cross section, and from here, right here, radius R. So what did you see? If R is 0, then so see, if R0, how much will be shear stress? You see 0.
0.
If so, shear stress will be maximum at the outer fiber, and at the center of the shaft, it will be 0. So we derive this formula, and we can go through the slide. I just give you the idea. Right over here, we just show you the application, the where this formula is applicable, right? You have a turbine rotating is generator, so you need a shaft, right? So in that case, you need to make sure the shaft will not be broken. Other example, you have a pump in your ground floor and run by electric motor, right? Pump is connected with the motor with a shaft. So if shaft is very brittle material, or you design very weak, what will happen? It will break down. Now, in this figure, you see at the outer page there is a little strip, right? Might be wood or whatever. But I give other example. Say you take 20 pencil, same size, all of 12 inch or 10 inch length. You band with the rubber band. It will be round, right? Then do like that. What will happen? You will see the outer pencil. They will move like that, like from here to here. Initially, you see they were straight, but like this one, initially was straight, but due to the bending moment, I'm not torn, they move over here. That means this one little bit there is some deformation happen, and this deformation kind of angular deformation. If I took a point right over here, you see, I'm like to see this one. So this one, his position after applying torque. So this line will connect with the center. But initially, his position was right over here. So if I add this line, so you see this much material move this by this much angle. Might be 10 degree, might be 5 degree, might be 3 degree from this point to this point. So this is called angular deformation due to the torque. You see, due to the bending moment, you have stress sigma equal to MC over I. And you have the deflection of the beam bend. But when you apply the torque, instead of bending stress, is developed shear stress. And instead of lateral deflection, it has angular deformation. How we figure out this angular deformation? That formula theta equal to TL divided by GJ. Okay. What is the T? Applied torque. What is the L? Length of the shaft. G is the shear modulus, is the constant, and J is the polar moment of inertia. So these two formula we derive with section A. Section B. So you just look through the slide. If you don't understand, let me know. I will explain it again. So right over here, we derive this formula. Okay, this one. And also we derive this formula. Theta equal to TL by GJ. If we look, we start from this figure. Okay, and in this figure, you see initially line AC was straight, but when we apply the torque, this was straight line AC. We apply the torque AC. If you look from here, this T rotating anti-clockwise, right? This line AC, it came in right over here. And this is the shear strain, and this much is the angular deformation, theta. And if I take tan gamma equal to base by perpendicular, right? So base is C prime, this length is AC, base. And AC equal to length of the shaft. So there is coming L. And C prime, this length will be, if this is theta, then R theta, the length of a circular R. So gamma equal to R theta divided by L. So by using this one and this formula, let me see. This formula, then right? And we know gamma equal to tau by Z. Tau by gamma, Z equal to gamma is the shear strength. So gamma value, you put it over here in the bottom, right over here. Tau equal to, put it over here, then you get this one. Then just rearrange, figure out value of theta equal to this one. Okay. So this mass we finish with section B. And also we finish one problem with eccentricity of column, and we solve one problem. So what we'll do, you look this video, still you have problem, then I will take a extra class. Obviously I have to take it, might be on Saturday. Do you have any problem if I take Saturday and extra class? Hello?
No, sir.
No, okay.
No, sir.
Good, thank you. So Saturday I'll take about might be 9 o'clock. I'll let you know in the night. Okay. So you can spend within 1 hour. That will be enough. And I'll clear all those 2 lessons. Some part of the column, some part of the torsion. Okay. So right now with these 2 formula, other thing that sometimes you might have multiple shafts, they attached together. Say one shaft right over here, it has a certain diameter, then other shaft over, they might have different material. So it's this shaft carry torque T right over here, this might be T2, and their orientation might be different direction. This might be T3. Now, in that case, you like to figure out the theta. How you do. So in that case, you need to draw a free body. So if I take the first part, it has a carrier torque. This is clockwise, so obviously this will be anti-clockwise. So this is T1. Similarly, you need to take the free body, figure out the torque right over here. Just make the free body. So it will have torque T2. Like you did free body of axial loading, right? Same thing over here. So we figure out theta for this one. So actually what I need to do, I need to figure out the theta, resultant theta of this whole shaft. So there will be, due to the torque, this will be noted by theta1, right over here, this will be theta1, this will be angular deformation will be theta2, this will be theta3, if you make the free body, right? Then resultant theta will be how much? Theta1 plus theta2 plus theta3. Some one might be noted clockwise, other one anti-clockwise. So if you think that the anti-clockwise is positive, then clockwise will be negative. So you have to take the algebraic summation. So for shaft 1, you will have T1, L1, G1 divided by J1, this shaft 1, plus you will have shaft 2. So torque T2, length might be L2, then G2, J2. Similarly, 3, 4, whatever you have, okay. And resultant angle, I know the theta. So this theta, they just write down a single formula. The theta equal to sum of TILI, JI, GI. And we'll solve some problem related to this formula, then it will be more clear to you. Okay. Now, we'll solve. Okay, remember, we need two formula, right? One formula tau. You apply torque in a shaft, shaft will experience not torque. Inside, you will experience shear stress. Okay, what happened? So, for example, somebody twist my hand. This portion I will not feel anything. I will feel light over pain because all the muscles try to tear, that will break down right over here. So same thing is we have a circular shaft. We apply the twist. Inside the material, shear stress will generate. So we need to figure out that shear stress magnitude. That is TL. I'm sorry, TR. So that will be TR. What is the R? Radius of the shaft divided by J. This is one formula. Other formula, angular deformation, theta equal to TL by GJ. Now, if you look all the truck running in Bangladesh, say people buy a 5-ton truck, but they load it with like 8-ton, 9-ton, right? So you see those shafts is rotating, right? That's why sometimes you might see, I see a couple of times, just by the roadside, you know, it break down the truck and the shaft is broken because it designed for 5-ton. What they do, they update the spring, increase the height, but they are not able to increase the capacity of the shaft because it is designed for 500 ton, or might be it has some safety factor, you know, factor of safety that they might design with 6 ton. But you load it, almost make it double. So their life is reduced. Initially able to carry the load, but supposed to be run for 10 years or 15 years, but after 5 years, it breaks down. Okay. So because due to the shear stress, and also there will be angular deformation. But angular deformation is very hard to see. Shear deformation is not that much. Okay. Depending on the length of the shaft and diameter, very hard to see in your own eye. But if you take softer material, like you take a rubber 2-inch diameter or 1-inch diameter rubber tube, solid tube, shaft, rubber shaft, do like that. Then you can see the easy angular deformation. What will do? You take a rubber, shaft. First, make a with the marker. We draw a straight line on the outer surface. Then do like that. Then you see how our red line is transferred. Okay, it's a deformation. So anyway, this problem is saying a twisting moment of 1100 Newton meters impressed and applied upon a 4.4 centimeter diameter shaft. What is the maximum shear stress developed in the shaft? That means they want what would be the value of tau in the shaft, right? They'd like to know. What is given? Also, they like to know angular deformation of the shaft. What is the value of theta? They like to know. What is given? G value is given. So what is this one? This one is T. And this one diameter of shaft given. So easily we can figure out value of R. R equal to D by 2. Right? And R equal to D by 2, then 4.4 you convert in meter divided by 2. How we can figure out the J? This for circular cross section, J equal to pi by 32 into D to the power 4. So easily you can figure out the J. You can figure out the then tau. You see, torque is given 1100 Newton meter. R 2.2, right? 4.4 divided by 2, 2.2 centimeter. Then you multiply by divided by 100, you get meter. Then you figure out the J, put over here. So shear stress is going to be Newton per meter square or Pascal. But next thing you need to figure out angular deformation, value of theta. What is our formula? Theta equal to TL divided by GJ. T we know 1100. J we can figure out because diameter is given. Value of G given. What is left? L is not given. So one thing remember, this theta will come out in radian, then you need to convert in meter. In degree. Okay. So they said angular deformation, but length is not given. If length is given, say for example, you are getting 15 degree or 15.7 radian. So you can easily calculate. But it's a length is not given. How do you do? So in that case, length is not given. So you figure out theta by L.
Sir, I have a question. Sir, do we need to change the gigapascal to pascal, or we can use the gigapascal?
Because a torque is given which you need, Newton meter, right? So G value also you need to convert in Newton per meter square by multiplying 10 to the power 9. Okay.
Thank you, sir.
So what is your ID?
Sir, 012.
012. Okay, good. I appreciate all of you ask questions and I give credit. Okay. So theta by L, then it comes T by J. Right? And what is the result? The result will be unit will be radian per meter or per feet. If you convert it degree, result will be degree per meter. That means, say after calculation, you got 5 degree or 2.5 degree per meter. What does it mean? If shaft length is 1 meter, then this much is the length. If it's 4 meter, then multiply by 4. Okay. So this way you calculate problem 1. Now we'll solve problem 2. Problem 2, it's saying a hollow 3 meter long steel shaft. So you see, you read the question, then figure out what is this data. 3 meter long. So this is L. transmit a torque 25 kilonewton. Again, you need to convert in Newton meter, multiply by 1000. So already saying torque, that means this data is T. T equal to 25,000 Newton meter. Right. The total angle of twist will not exceed 2.5 degrees. That means this is theta. Theta is given. Theta is 2.5 degrees.
Sir, your microphone is off.
Okay, sorry. So you can see now, right? Hello?
Yes,
You
sir.
can see? Okay.
Yes.
Okay, so let's see, we solve this problem 1 second. So it's saying length of the shaft is 3 meters. So we'll have the value of L. This one, value of T. Obviously, you need to convert in Newton meter. And it's saying hollow. What does it mean? We have outer diameter, also it has inside diameter. And this angle is given theta. It's a allowable shear stress of this shaft 90 megapascal. That means you cannot apply shear stress more than 90 megapascal. So that means maximum tau is given. Max tau equal to 90 megapascal. So you need to multiply by 10 to the power 6, then you have Pascal. Determine inside and outside diameter of the shaft. You need to figure out this diameter, outside diameter. If I say D naught, I need to figure out this diameter, D high. And what is given? Value of G equal to 85 megapascal. Converting 10 to the power 9, multiply 10 to the power 9, that will be Newton meter square. Okay. So let's solve it. So you remember two unknown. We need to figure out this one and we need to figure out this one. So we need to have two equations. You see, one equation we have tau equal to TR divided by J. So this R, I can write down R equal to D naught by 2. And J, pi by 32, D naught to the power 4 minus DI to the power 4. And other formula, theta equal to TL by GJ. By solving these two equations, we can figure out the value of D naught and DI. Okay, so let's see how we can solve it.
Sir, are we changing the theta into radian to solve the math, or we are using the theta in degree?
Theta, we have formula, right? You are getting theta equal to TL by GJ, right? So when you use this formula, that theta equal to TL divided by G into J, this will give you result in terms of radian. Okay. Then
Yes,
you need to convert in degree. You understand?
Yes.
Okay.
Yes,
Yes,
but
sir.
postponed we have theta in degree. Do you need to change the theta into radian to solve
Yeah.
the math, or we can
When
use
you,
That
when
means
you
do we need to use 180 by pi?
yeah, like to write this problem, we have theta 2.5 degree. How we can convert in radian? We multiply by pi, then divided by 180 degree. So that will give you radian. Okay. So in this problem, we say hollow shaft 3 meter long. So this is our L. L is given, length of the shaft. torque 25. So 25 kilonewton meter. I multiply by 1000, it comes Newton meter. Then angle of twist 2.5 degree, right? So I convert in radian. If you don't convert in radian, then you put in the formula, your result will be wrong. Okay. Allowable shear stress, it's saying right over here, 90 megapascal. So tau equal to 90 megapascal, you multiply by 10 to the power 6. So 90 into 10 to the power 6, 7 Pascal. Value of G is given this one, 85 gigapascal. You convert in Pascal. What do you need to figure out? Inside diameter, D not equal to outside diameter, D not equal to how much, and DI equal to how much. That you need to figure out. So we use two formula. This one and this one. Obviously, we have only two formula. These two formula in the torque main formula, and we have two answers. So at first, you use this one, tau equal to TR by Gz. What is the R? Where tau will be maximum at outer fiber. Even they are saying is hollow. So how much will be shear stress at the center? Right over here. Anyone?
0.
0. No material, right? So shear stress will be something over here, then gradually move up outward, right over here to the maximum. So value of R will put D naught by 2, right over here, D naught by 2. This value we like to substitute right over here. And what is the J? J pi by 4, D to the power 4 minus DI to the power 4. Because since this is hollow. And tau value is given. So everything you put over here. So you will get, this is tau. This one you will get value of torque. And this is value of R, D naught by 2. Okay, D naught by 2, right over here, J. Now we simplify this equation, you will get this value equal to this one. I'm saying this is equation 1. Now we use second equation. Yes. Any question?
Sir, this pipe is, yes, sir. This pipe is hollow. That's why we are taking only D naught. But if there was a material like two materials, then what should we do?
Always you have
It
to take
wasn't
the,
hollow. Suppose it was hollow.
suppose it
Outer
is not
diameter.
hollow, right? Say
Yes,
this
sir.
one, not hollow. So where will be maximum? It's saying the maximum shear, it can take 90, right? 90. So in this shaft, say this is right over here is radius, center. So where will be maximum? Now, obviously at the outer fiber. So you will take outer fiber
At
mean outer radius.
at the end.
What do you say?
But if there are two types of material, the inner material is one type and the outer material is another type of
Okay.
material.
Now, your question that there might be
Two types of
a
material.
composite shaft, like
Yes, sir.
this one. Inside is might be soft material, outside hard material. So in that case, you need to check both one, because the inner one, his shear stress will be 0 at the center, and right over here it will be maximum,
Maximum.
right? So you'll figure out right over here, and you'll see since they're two different material, make sure it is not exceed. It should not be more than the allowable of the material. Same thing for outer, what will be maximum? Over here will be minimum, over here will be maximum.
Maximum.
Then you take that one. Okay. But since this is the same material, just hollow, so we know right over here, your shear stress will be maximum. So we took R equal to D naught by 2. Got it?
Yes, sir.
Now, so for this problem, if I say the figure out the I am saying to figure out the torque, how much torque it can carry. This type of problem. It's a outer shaft, hollow shaft is made of steel, inside one made of aluminum. I give it the allowable and I can say figure out the torque that maximum shear stress in the inner shaft will be this much. Okay, then you need to go with that one. Anyway, so right over here, you put everything. This is the value of the J. Then tau value is over here. T value is given. So you put in the equation, you get this one. And now I see right over here D naught. You cannot solve it. Okay. So now you use the second formula. Second formula, theta equal to TL by GJ. So what is our theta? 2.5 degree. I already convert in radian. So this is in the radian. T already given. L 3 meter is given. G value is this much in Pascal. Now J value we don't know, right? We just put pi by 32 d to the power 4 di to the power 4. Now we simplify this equation. You get this value equal to this much. Now this value you put it over here. Then you can calculate D naught. So D naught I got this much meter. And this D naught, if you put over here, you will get DI. So DI equal to this much meter. Then you convert in millimeter because this value is very low value, 0.14 meter. So it is coming, I make it round 146 millimeter. This one I make it 125 millimeter diameter of the shaft. So any question? Any questions from here? Anyone? Any question?
No, sir.
No? Okay. Do you have any class after this time?
No, sir. We have